Hi, this is Barrett Givens, and in this video, I want to show that the surface of a sphere and the surface of a cube are homeomorphic. That is, they are topologically equivalent. And I've drawn here a unit sphere and a unit cube, okay? Actually, I guess it's not really a unit cube. It's a unit sphere, and then it's a cube with two units on each side. So the origin is kind of like right in the middle here, and this cube goes out to 1 unit away from the origin in like 6 directions. All right. They don't necessarily look like they're the same. I mean, the cube has got these like sharp edges and corners, and the sphere is just nice and rounded. But the point is that they're both sort of a surface that kind of like fully encloses a region, I guess, is the way to think about it. So to show that they are homeomorphic, I need to somehow find a function that either takes points on the sphere and sends them out to the edges, the sides of the cube, or I need to take a function that goes from points on the cube and then sends them inside to the sphere, one way or the other. It turns out to be a little bit easier to start with points on the cube and then map them onto points on the sphere. So I've drawn some pictures here to kind of show what I'm going to do. What I'm going to do is I'm going to take any point on the cube. So for example, let's say this point right here is a point P on the cube. Okay, that one's on the side wall of the cube. I'm going to shoot a ray through P into the origin, and that ray will intersect the sphere at some point. That ray will intersect the sphere at some point right there, which I will call F of P. Okay? If I were to take a point on the top of the cube, let's call that point Q up there, and then shoot a ray through that point Q down to the origin, it'll cross the sphere, the surface of the sphere at some point. So I'll call that point F of Q. And then finally, I have a really similar one down here. Let's call that one T maybe. And then that will be F of T. But the general method is for any point on the cube, shoot a ray through that point down to the origin, and then see where that ray crosses the surface of the sphere and make that the output. And it turns out that we can do this in a way by just taking the distance from that point to the origin and then just scaling it down by that distance. It's kind of like the same process as making a unit vector. In fact, it is the same process as turning a vector into a unit vector in the same direction. So we take the magnitude of that point, x, y, z. So the point x, y, z will be the point on the cube. Take a point x, y, z, which is a point on the cube. We take its magnitude, the vector from the origin to that point. Its magnitude is the square root of x squared plus y squared plus z squared. And then we scale by that. And so that's going to shrink that down to a unit vector in the same direction. Because it's a unit vector, it will land on the surface of that sphere if I'm assuming that the sphere has radius 1. Okay. And so that is a continuous function as long as we're not dividing by 0. But since x, y, and z are on the surface of the cube, x, y, and z can't be the origin. So this is a continuous function. Um, is it one-to-one and onto? Yes. You have to think about that a little bit, I guess. If you take, if you imagine having two distinct inputs, like if I took another point right here, x prime, y prime, z prime, it's going to intersect the sphere at a different point. You have to sort of convince yourself of that. I think maybe I won't try to fully write that out in this video, but it is true that it is one-to-one, that if you take two different inputs, you will get two different outputs. It's also onto. Probably the easiest way to see that is to think about what its inverse would look like. And again, I'm not going to write down the formula for the inverse because I think it will get messy. But what would the inverse be? Like, how would you just describe the motion of the inverse? So for the inverse, we want to start with a point on the sphere. So start with a point on the sphere. So maybe like right here. I'm going to shoot a ray out from the origin outwards now, and then keep going until I hit the surface of the cube. Will I always hit the surface of the cube if I shoot a ray from the origin out through the sphere, touch a point on the sphere, and then keep going? I will hit the cube at some point, right? And there would have to be some kind of complicated formulas to figure out whether or not you were coming out the front, back, left, right, top, or bottom sides of the cube. But you could divide the sphere up into the different regions that correspond with those different parts. and then say, okay, if you look at a point on the sphere, first figure out which one of the three or the six sides that you're on. And then depending on which one it is, then you could figure out, okay, that means I need to scale this until I can get, maybe the Z coordinate to be one or the X coordinate to be one. So for example, for this front face, the X coordinate is one. If I'm looking at this front face right here, so I would take my ray and then I would scale it out by whatever I needed to multiply by to get the X coordinate to be one. And if it were this left face, I would scale it out until the Y coordinate was -1. And so I could take any point on the sphere and then I could scale it by the appropriate amount to either make the X, Y, Z coordinate be 1 or -1. All right, so I claim that it is invertible. I know that this one's a little bit hand wavy, but we're describing it more as an action rather than via a formula. Okay, so this function is continuous, has continuous inverse, and it is one-to-one and onto, and therefore these two surfaces, the surface of a cube and the surface of a sphere, are topologically equivalent. Okay, thank you for listening.